Hello everyone. Let's continue our discussion with data update operators, which are delete, insert, and update. In this session, I explained the basics of update operations and how they can quickly become complicated. Why become complicated? Because they need to update existing indexes, access multiple tables, and enforce existing constraints. Also, we will dive into Halloween problem and resolutions for this problem in SQL Server. Let's get started. Update plans can be complicated because they need to update existing indexes alongside data. Also, because of objects such as check constraints, triggers, update operations and execution plans might have to access multiple tables and enforce existing constraints. This can have a big impact on the performance of the entire update operation. We will take a deeper look at that now. Let's run this query now. As you can see, the first step in this plan is accessing country region table to pick the record to delete. However, before deleting, we are accessing three additional tables: state province, country region currency, and the sales territory. The reason behind this is that these three tables have foreign keys referencing country region. So, SQL Server needs to validate that no records exist on these tables for the specific value of country region code. Therefore, the tables are accessed and assert operator is included at the end of the plan to perform this validation. If a record with country region code value which is being deleted exists in any of these tables, assert operator will throw exception and SQL Server will roll back the transaction. For this, we are using nested loop operation here. Let me show you in this way. Firstly, by going through the clustered index, we are picking up the row to delete. Afterwards, by using nested loop, we are checking whether there is any same foreign key related record in these clustered index tables. Here, we are using index seek, which is very efficient. If yes, our query fails. If not, we go next loop to check next indexed table. In the next nested loop, we are checking the table by using index scan, which means we are going through all the records. In the same way, next nested loop operation happens on the next table. If there is no any same foreign key record, this validation passes and record is deleted. This example shows how integrity constraints like foreign key can make delete operations more complex. Let's run this query. As you can see here, we are scanning table and updating row by row. Now, let's add an index. Here, now our execution plan is changing with table spool. For now, just understand that table spool is just a temporary table where SQL Server is saving the records which is being updated. After generating this table spool, records are updated one by one without accessing clustered index again. If we explain the architecture, we can come to this flow. In table scan, we find target rows to be updated. Then, by using compute scalar, we update these rows and then we change these rows in table by using table update operator. After creating index, however, we are saving the target inputs in table spool temporarily, and then we are updating the rows and finally the target table with index. Here you can spot that we are not updating the rows directly from indexed table, but we are creating table spool first and updating. Why? Reason is Halloween problem. Let me explain this problem. Suppose we have this table and want to increase employee salary by 10% one time only, okay? If the salary is lower than $25,000. In this case, SQL Server changed the target rows row by row in 3 rounds. In the first round, target rows are defined. In the second round, row is changed. In the third, next row is changed. This happens when we have heap table without an index, and we call this process row by row change in SQL Server. Now let's create clustered index on customer. In this case, rows become sorted. In the second round, there are two steps. First, 21,000 is increased by 10%. And second step is resort the table as the number changed. We should do resorting as there is clustered index here. In this case, now 22,000 is becoming first row. Third round, we should change second row, which was 22,000 before, right? And due to resorting, 23,100 is the second row. As a result, we mistakenly increase the same value again. This is called Halloween problem. As this was why Halloween problem we call it? Because this was discovered on Halloween day, as far as I know. And in this case, what SQL Server does it creates a copy of the table in the working table in temporary database, and while updating the customer table in the second and third rounds, it does not reference the main customer table but heap table. Since heap table is not resorted and does not change, SQL Server does not confuse row order. This was Halloween for update statements. In the case of update, Halloween might happen when you have clustered or non-clustered index only. Let's now see Halloween in insert statements. Suppose we are running this statement, inserting employees to employees. Okay, the same table we are again inserting. We expected this outcome. However, this does not happen. In the first round, first value is inserted. In the second value. In the third value. However, database does not recognize that this is newly inserted value and mistakenly can continue inserting newly inserted value again and again. This can continue forever in the loop. Unlike update statements, Halloween problem can happen in both heap and indexed tables. SQL Server can deal with this Halloween problem in the same way as Halloween in update statements, like using table spools. Other than table spool, SQL Server has multiple ways to deal with Halloween problem. For example, for update statements, SQL Server can use table or indexed scan instead of indexed seek operations on problematic index. Or it can use hash match join and make problematic table as build table. Or it can use a redundant sort operator after seek or scan on problematic index table. The choice of these operations depends on the cost. Let me show you. Let's run this command. This is an example of table spool, which we already discussed. Here, SQL Server is preventing Halloween with table spool. If we adjust this, we just change this number to 50, our query plan changes to hash join. Here, we are creating hash table only once and doing insert operations based on this hash table. Since this hash table is built only once and does not change, we can prevent Halloween problem. Next, let's see this example. Now, here our operation is changing to sort operations. Here, we are bringing data to sort operator only once and sorting, right? Afterwards, this merge join is happening only once and we are doing insert operation. Starting from this sort operation, all the operations are done once. We don't access to the original table to pick the values. Therefore, we can prevent Halloween issue here.